Okay, now in this lecture, I want to go over some generalizations of our previous discussions. And one thing I will talk about is that the compressible problem. Yeah, sorry. Okay, compressible flow. Okay, so water in a consolidation system, in a solid mechanics problem, we are assuming that water in general is incompressible, which make a lot of sense as water are much. If you compress a bed of water, let's say you put water into a plastic bed and you try to compressing it, you rarely really reduce the volume of the water, but instead you trigger the water flowing, right? Okay. So, but in some other case, okay, for example, gas. So if the porous media are saturated with gas, okay, or air, they are actually still, strictly speaking, porous media, okay? But then the gas would be much easier to compress than, say, water, right? Okay, so or in any other case, when we suggest to some extreme pressure, then the water, then the compressibility of the water and even the solid will become important. Okay, so here we need to talk about, we need to make some assumptions about this, and then we can talk about the compressible flow. Okay, so what previously in the incompressible flow? In the incompressible constituent, we are assuming that the rho s is actually equal to the initial rho s. Okay, the intrinsic one is actually equal to the intrinsic solid density is equal to the initial intrinsic density, and then the fluid is actually equal to the intrinsic one. Another way to say that is that the rate of change of the rho s and the rate of change of the rho f is actually both zero. Okay, does that make sense? Now, the partial s dot is not necessarily equal to zero. Okay, so the partial density change is actually equals to the volume fractions of the solid, the change of it, right? Okay, and then the fluid partial density is equal to the change of the porosity times the intrinsic density. Okay, so again, intrinsic density is the mass of fluid divided by the volume of fluid. Okay, so and the partial density is actually mf divided by vt. Okay, so far so good. Now, in the compression case, what we actually need to think about this is the following. In the compressive case, what we have is that rho s dot is not equal to zero, rho f dot is also not equal to zero. Okay, that's obvious, right? Okay, so what will they change? Okay, so let's look at the balance mass, and then we can see the extra term. Okay, so let's write the balance of mass. Okay, so the balance of mass, as we recall this, is equal to the density, the time derivative of the volume fractions times the intrinsic density plus the volume fractions times the intrinsic density times the divergence of the velocity of the phase equal to zero. okay? And here I'm consider only two phase, alpha equal to S, solid or fluid. Okay, so far so good. Okay, basically just these two terms. Okay, let me take out this term. Let me apply the product rules for this term. So what I would have is that I take the first derivative on this, and then I roll alpha times the derivative of the volume fractions plus the second term. Now I take the derivative on this term and then take this term out. That would be the volume fractions times the rate of change of the density itself. Now this term previously in the incompressible case is simply 0, right? Okay, now it exists. And plus the term that we already have in the previous derivations, the divergent term. Okay? So far so good? Okay, this is just coming from the product rules. Now we need to deal with this term. Okay, how does the density change? Okay, so how can the density change? Now, this is the intrinsic density. The intrinsic density is equal to the mass divided by the volume, okay, of alpha. Now, which one is changing in a closed system? In a closed system, you have the same number of molecules. Can you change the mass? You cannot change the mass, so the only thing you can change is the volume. Okay, does that make sense? Okay, well, strictly speaking, okay, sorry, let's not do this strictly speaking thing. Okay, so we have the volume that could change. How do I change the volume? Okay, so assuming that is ideal gas, how would you change the volume? So there are two things I can change to change the volume for ideal gas. What is that? Sometimes in some case we call it equation of state. What is the fundamental variable of equation of state? We have the volume, we have the pressure, and we have the temperature, right? Okay, I can change the temperature. That would actually change the density, okay? I can change the pressure. I can change the pressure. I would also change the density, right? Okay, so it's like if you're climbing, if you're staying here, you would actually the boiling temperature of the water is actually different than when you climb a very high mountain and then you try to boil the water again. The boiling temperature will reduce, right? As you go higher altitude, right? So what happened to the higher altitude? When you're at higher altitude, what happened? Yeah, so in the case where you actually have less pressure, then the phase diagram change, and here we would not consider a dramatic change of the temperature for most of the groundwater problem. Okay, if you're motoring a nuclear reactor, you probably need to care about the temperature. But in most of the applications, we were assuming that the temperature change is relatively gradual. Okay, so go back to this. Okay, so what I actually want to do here is to first further simplify the equation a little bit. I will take the whole term divided by times the 1 divided by the intrinsic density itself. So put it to here. So then the equation is read as the following: the change of the volume fractions over time is plus the change of the volume fraction divided by density times the rate of change of the intrinsic density plus the volume fraction times the divergence of the velocity itself of the phase is actually equal to 0. So these three terms. Okay, so what I actually want to do in this particular case is to deal with this term. What I mean by deal with this term is that I want to rewrite this term as a function of P alpha. Okay. Why do I want to write it as a P alpha? This is just for convenience, because actually I want to write a UP formulations. Okay, so the pressure term would be more convenient than directly putting the density as one of the variable. Okay, so how do I do that? Okay, I need to have something called a constituted law. Okay, this is actually not direct. We plug it back to here. Okay, so this whole thing is the additional term for the compressive flow. Okay, now with this one getting defined, okay, we can actually rewrite the balance of mass with the unknown that are more convenient for us to write by the balance principle. Okay, so let's consider the ideal gas case. We call that P times volume equals to RT. What is the term for R? Yeah, Avogadro number. So this one is actually a constant. Okay, sorry, can you? So, and this one, if we are assuming that T is actually changed very small and R changed very small, then we have a constant. And this is actually called barotropic flow. Okay, so for barotropic flow, we have a very simplified version is that we will say that P is actually proportions to 1 divided by V. Okay, so because it's proportion to 1 divided by V, and the density is actually m divided by V, and m remain constant, so we have a very simple relationship is that P is proportional to rho of alpha. Okay, so does that make sense? Basically what it means is that it's very simple. If the pressure increase, then the density also increase. Does that make sense? Okay, it's just intuitively that will make sense. Now, if this is actually the case, then what we actually want to write is that we would actually write the density of the intrinsic density as a function of P. Okay, does that make sense? Or we can actually also write the inverse, assuming that inverse exists. Is that P is actually also a function of the density. Okay, so this trick is also used to model frozen soil, except in the frozen soil case, we would actually need to put back the temperature, because in the case that if you want to model the frozen soil, there's a phase transition there, so the temperature must be taken into account. Okay, but what we actually want to write in those cases is to write the entire phase diagram, which actually requires us to consider the relationship between pressure, volume, and pressure, volume, and temperature. Okay. Now, if I take a derivative of it, okay, with time, then what I would have is that the change of the density alpha would be equal to the change of the density with respect to pressure Let me write it this way. Okay, so this actually should be D. Parcel. Okay, does that make sense? So far, so good? Now, let me rewrite this as just P prime P. I mean rho alpha prime. Okay, just for making it simpler. So we will have this. And then I have sorry, I have the whole thing divided by 1 divided by a rho. Then I'll have this term. So far, so good? Okay. So you may wonder why I actually did that. It looks very redundant, right? Huh? Yeah, that's a good guess. Whenever you have the 1 divided by something, you kind of prepare to have the log and then you integrate it. But here I actually doesn't necessarily want to do that. The reason I actually want to do this is for another purpose. I want to be able to write this whole thing in terms of for the UP formulations. Okay, so what is convenience for the UP formulations? I need to write everything in terms of P, and I want to write everything in terms of solid displacement, right? Okay, so what can give me the displacement, or maybe not necessarily a solid displacement, some kind of displacement functions. Okay, so if you take a derivative, you get the strength, right? Okay, so now here, if you look at this expression, there's no way I can put the strength here, right? Okay, so P is good. Okay, I want to keep the change of the P term. But what I actually don't want, or this is a little bit inconvenience, I need some more deviation, is that I want to get rid of the intrinsic density and replacing it with the strength, right? How do I do it? Now, intrinsic density cannot be rewritten as a strength, but change of the volume can be rewritten as the change of the strength, right? Sorry, the change of volume can be written as the change of strength. Yeah, exactly. So the strength rate is related to the change of the volume, right? Okay, so here, then what I actually want to do is the following. I just need to substitute rho alpha equals to m alpha divided by v alpha, okay? And then I change the variable again, okay? So if I substitute it here, what I would have is that the change of the volume, the change of the intrinsic density over time would be equals to the volume times the change of the mass divided by rho t minus m alpha, the time derivative of the volume over time, divided by the volume, the entire volume square. Okay, I won't go for the details, just substitutions. Okay, and then applying the chain rule. Now notice that the mass doesn't change over time. Okay, in a cold system, the initial mass and then the final mass is the same. We cannot create or destroy mass in a cold system, so this one go to 0. Okay, and this whole term, including this whole term, go to 0. Okay, and then I still have the m and then v left, but if I take it out, I would have m alpha divided by v alpha times 1 divided by v alpha times the time derivative of v for the alpha phase. Okay, so far so good. Now, this one is simply equals to 1 divided by rho alpha again. And what is this term? Okay, it's the change of the volume divided by the volume. So what is the strength for one direction? The strength of one direction is the change of one direction divided by the original length. Okay, so if you consider a box, okay, what is the strength in the axial term is actually the change. Let me write a little bit, maybe something like this. Okay, so this is a new triangle, right? Okay, so what is the change of the volume in that box? Okay, I measured the new height and then the original height, and then also the wave. Okay, I measured the 3 dimensions and then the change of them, divided by the original length, and then times each other, then we get a volume, right? So this whole thing, if you put it here, is simply the change of the volume. Okay. Now, if we get to that, then what actually happened is that we will come up with the following term: 1 divided by rho alpha times the time derivative of the rho alpha divided by 1 divided by tau is actually equals to 1 divided by V alpha, and then notice that there's a minor term there, times the V alpha VA. Okay, so if we rearranging the term, what we would have is the following. Okay, so let's see. Yeah, and then we will have minor partial derivative of P alpha divided by that over respect to time times the rho alpha prime P alpha equals times the derivative of the the derivative of the volume of alpha phase over time. Now, this term is actually the Buck modulus of the alpha phase. Okay, can you see that? Just based on the previous assumptions. Okay, so this one is actually the Buck modulus. Or more accurate, the intrinsic Buck modulus of the alpha constituent. Okay, Okay, this is very confusing, but one thing that are very important to know is that this term is actually not the Buck modulus of the solid skeleton. Okay, so let me put the thought experiment. I have those particles. Let's say I have this porous media, okay, with 3 pockets. And then the representative volume, I will draw a circle to represent this RVE. Okay, this RVE can be again compressed or extend easily because there's a pocket here that I actually have nothing but gas. Okay, now I can change that circle easily by not changing the size of individual grain or water. Okay, but I can also change the size of the circle. This doesn't look like a circle, but then the surrounding of the blue enclosure by simply shaking the grain, right? Okay, so those are very different. Shaking the grain, changing the size of individual grain are actually much more difficult than changing the entire assemble. Okay, you see what I mean? The size of the assemble. Now this Buck modulus is actually, let me write down this. This is related to the density divided by the change of the density for the barotropic flow, and it's actually also equal to the change of the density times the pressure that changed the the change of the pressure per density here. Okay. Yes. Now, what we actually need to go so far is to go through this to write the finite element problem. In this case, I will write the balance of mass as the following. I write the solid phase as rho s, as the volume fraction of the solid divided by the Buck modulus, intrinsic Buck modulus of the solid phase times the divergence of V, okay, times the volume fractions of the solid. And I write the fluid part in the same manner. Okay, so far so good. Now notice that to change the mass, what the equations here looks very dry, but they're telling you 3 different mechanisms, okay, that you can allow you to change the total mass of the individual phase of the system. The first term is to change the volume fractions, which makes sense, right? If I change the proportions, the ingredient portions of the material, I will change the mass phase of that in that particular phase, right? Okay, I make a cake with 3 eggs compared to 2 eggs. I have a different portion of the egg, right? I just change the proportions. The second one is actually representing the deformations or the compression of extension, more accurately, not deformations. The compression and extensions of individual phase, okay? For example, I have let's put the imaginary example. I have a sample saturated with water of a particle, but that particle suddenly shrink, okay? Okay, or actually expand because it absorbs water or whatever, okay? So then that would be in this term. And then the last term is the movement in and out of the system, okay? Captured by the divergence of V, okay? You see what I mean? Or the relative the change of the velocity in all three directions combined. Okay, does that make sense? The divergence is actually simply just the diagonal term of the gradient add together, right? Okay, so there's a free mechanism. If the material is incompressible, then the second mechanism is taking off. Okay, so does that make sense? Then I go back into there's just two options for me to actually change the total mass of the system. Okay. Now, if the material is incompressible, and undrained, then what happens? If the material is undrained, all the possibility of water getting out is taken out, so there is no relative velocity, so I'll Q off this term. Then what happened to this problem is that this system become an ODE. Okay, there's no spatial derivative anymore. Okay, so can you couple a PDE with ODE? In principle, you can, but you have to think about what happened to the field. Is it stable? Okay, because there is no spatial relationships in the ODE. Okay. Okay, so let me put some number so that it's actually more meaningful. So in many cases, in the 1 atmosphere, the Mach modulus of a water is about 10 to 7 kilopascal, or actually you can think about how many megapascal. Yeah, close to 10 to 4 megapascal. How many gigapascal? Huh? 10, yes, exactly. I just keep minor to you, right? Okay, so does that make sense? Okay, so for the silicon, which is actually what sand, for example, could be made of, it's actually about 100 times more stronger than the water in terms of Mach modulus. Okay. Of course, this number change depends on the temperature. Okay. So as a result of this, so we can actually write, if you write the rho s times T plus rho s by V equal to 0, then what we get is that we will get 1 divided by rho s, rho times the partial derivative of rho s, the rate of change of it minus the divergence of V. Okay, so for the solid skeleton, or for the solid matrix, we would have PS equals to as a PS as a function of rho s, and the volume fractions of the solid. And if I actually take the time derivative of it, I would basically have two different terms, because it actually depends on two different variables. The intrinsic density and the change of the volume fractions. Okay. So let's call these equations star. Okay. And let's put these equations maybe as the double star. And then let's put the two equations as the triple and a quadruple. equal star, then what we have is that if we combine the whole equation together, then what we have is that the density of the solid, the time derivative of it, is actually equals to the partial derivative of the PS with respect to the intrinsic density times minus P at rho S divergence of V plus rho PS divided by this. Okay, so far so good. Now, just bear with me. Just want to derive the relationship between the intrinsic modulus and the Buck modulus of the solid matrix. So, if you actually write out the equations previously, what we get for the Buck modulus. We will have this term. And if I substitute what I have from the previous equations, eventually I will get that Buck modulus equal to the volume fractions of S times these expressions. Okay, so this is simply just the algebra. Okay, so why do we care about these two terms? This is actually the Buck modulus of the solid matrix. Okay, now this look very ambiguous, but there's a few highlight here. You see the K here. Okay, this is actually the K we talk about for the entire ensemble. Okay, and this one is actually the Buck modulus of the individual solid grain. Okay, so assuming that all these terms are positive, okay, so what can you tell about the relationship between Ks and K? We can't say that much yet, okay, but if you substitute some number, okay, then we would actually be very clear that the Ks is actually much larger than the K alpha. In fact, the Buck modulus of the solid matrix cannot exceed the Ks or the Kf. Okay. So if I substitute it back into the balance of loss, balance of mass with this new term, then I come up with a new term that actually explain what I have from the previous coding sections. The balance of mass in this case, in the compressible case, we will written like this. For the solid phase and for the fluid phase, I will have this term. Okay. Now, sometimes people write it as a B, okay. The whole term K divided by Ks. Okay, if you remember, the Bill's coefficient is actually 1 divided by K divided by Ks. Okay, so that's the Bill's coefficients, which I will explain why. You would actually have the 1 minor term here. But this is actually different than what we have before as the additional term that we need to consider. And then this is also another term that actually also coming up from the pressure term, from the pressure of the fluid. Okay. Now, why do we care about this? So what is the corresponding incompressible flow equation for this? When I combine these two terms, I simply have the divergence of V, which is actually the solid, plus the divergence of the Darcy's velocity equal to 0, right? Do you remember that? Okay, now I have this extra term. Okay, what would be the implication of the matrix system? Okay, previously in the undrained case, I simply have divergence of V, right? Okay, now even in the undrained case, I actually have something that are compressible, right? Isn't it? Okay, because divergence of V equal to 0 imply incompressibility, right? Okay, because if I changing these directions, it's compensated by the other two directions so that the sum becomes 0. Okay, so I did not change the size at all. But here, even in the undrained case, I can actually compress the material a little bit because this term is actually not equal to 0. And then in the matrix system, that would give rise to the, where would this term come up into the UP formulations? Okay, so in the UP formulations, we have that that first term is actually coming from the solid. Okay,Cijkl, blah, blah, blah. And then I have this term that are the B matrix. Okay, depends on how you want to write the B. Okay, and this one initially is just the omega term times delta T, right? Which is actually just coming from here. Now I have this term. Then what they give it to me is the extra file element term that are actually written in terms of P, even though the permeability equal to 0. Okay. So is it a good or bad thing for the insub system, for the matrix system? Is it good or bad? Well, I guess it depends. Okay, but let me look at it more carefully. Okay, let's consider a special case of undrained case. Okay, what is undrained is the following. Undrained translate to no flow in and out of the system. Okay, the water is trapped. Okay, this is what undrained case mean. So what actually it means is that either K equal to 0, the permeability, go to 0, that will give you an undrained case, or delta T is actually approaching 0. Okay, does that make sense? Okay, like in the consolidation problem, you suddenly applying a load at the very first step, the water haven't diffused yet, so you have a second of undrained case in a very short period of time. Okay, in this case, if the water is trapped, then actually what happened to the water and the solid is that the velocity of F equal to the velocity of the S, the fluid and solid, move together because they're trapped together, right? Okay, you cannot move outside the frame of the solid skeleton. Okay, so they're equal to each other, and then they just simply equal to V. And or the other way to say that is that Darcy's law equal to 0. Okay, Darcy's law is the relative velocity of the VF over VS, right? And so what actually happened is that the relative of the respect to the s and the derivative, time derivative respect to the f are simply the time derivative. Okay, there's no difference between the two because they follow the same trajectory. They move together, right? So there's no need to distinguish them because the convection term will be identical. Okay. Now, if we add these two things together and I add the term b there, then what I will have is that I will have 1 minus b divergence of v plus rho plus the porosity divided by kf times the Passer change over time plus the divergence of v equal to 0. Okay, so in this particular case, what I would have is that I would simply have have this term coming out on the one side, and then the other term would become 1 minus small b times divergence of v, and this one 1 minus b equal to 1 minus k of the solid skeleton divided by the intrinsic bulk modulus is actually called the Beal's coefficients. Which is actually, I believe it derived it while it's a faculty at Columbia University. I forgot. When is the paper published? I think it's 60 something, so I need to check. Maybe I would know the answer after the break. Sorry about that. So this is actually the relationships. The change of the water pressure in this case is related to the change of the solid skeleton times this whole factor. Okay, does that make sense? That only makes sense if you cannot allow the water to get in and out, okay? It's like orange. If you haven't peeled off the skin and then you're squeezing it and then there's no juice coming out, okay? Then you can actually using the deformation of the orange on the surface to determine what is the pressure inside, right? Okay, you see what I mean? If you leak out, of course you cannot, right? Okay, is it a good example? Okay, you get the idea? Okay, so far so good. So now what happened when the b equals to 1? So when b equals to 1, when the solid phase, so if Ks go to infinite, okay, and Kf is actually still finite, then what happened is that K divided by Ks would approaching 0, okay, and so Beal's coefficients then become 1, right? Okay, does that make sense? Okay, so now if this is the case, then this one is actually simplified as the Kf divided by the density, the porosity times the divergence of V. Okay, now this is very important. In this case, in these functions, the change of the pressure of the fluid depends on the bulk modulus of the solid and the bulk modulus of the fluid, okay? But if you look at the equations, okay, so it's actually linear to the Kf, okay? Sorry, so on the other hand, Kf is actually part of the slope of the volume of change of the fluid. Okay, so strictly speaking, this is not a linear functions because the porosity of rho f is actually also depends on the P itself, right? Does that make sense? Okay, but if you're assuming that the wall ratio is not changing that much, you can assume it's constant. But that won't for modeling something that a pole collapse or suddenly there's a big change. Okay, so that nonlinearity had to be taken into account. Okay, so but if the water if the solid skeleton is rigid, okay, sand is a good example where you can comfortably assuming that the individual grain are rigid, and then the change of the pressure is actually related to the density, is actually related to the change of the volume times Kf divided by rho f. Okay. Why do we care about this? For gas, for example, why do we care about this? So this is related to the acoustic, right? Okay, if you want to develop something that is soundproof, right? Okay, then you actually need to take account of what happened to the Buck modulus. What happened to the wave propagations, and that would be something that, for example, you need to take those things into account. Okay, but the conclusion here is actually very simple. If I change the F a little bit, then I would actually have to change the volume of the fluid. Okay, is a given. Does that make sense? So every time I change for the material that are compressible, to change the pressure, I would actually lead to the change of the solid skeleton. Okay, when the material is actually undrained. Okay. Sometimes we call it undrained limit. Now, if it's actually not in the undrained case, you allow water to come in and out, and you try to apply the pressure to the system, you would get a combination of the change of the volume and diffusions. Okay, so you basically have a budget for the external work you apply. It either lead to the water move within the material, outside the material, or you lead to the compactions of or expansions of the material. Okay, depends on what kind of loading you put in there. Okay, so let's take a 10 minutes break, and then we come back at 11:25. Okay. Okay, and then so let me finish the derivations for the compressible flow problem. Okay, so previously we actually have defined about the compressible flow for the different phase. The solid phase can be written like this. Okay, and the solid phase, and the fluid phase can be written like this. Okay, if you pay attention, you may already notice that here I keep the perspective of the fluid derivative over time, and here I did not put anything for the solid. Okay, if you remember from the previous lecture, we would follow the solid trajectory for these formulations. Okay, just simply because we want to write the material law in the solid phase, just more convenience. Okay, there's no right or wrong. If you like, you can follow the fluid phase and then treat the solid as a relative. If you for some other case, just for convenience purpose, we pick the solid. Okay, now I cannot combine these two equations because I have two different type of derivative, right? Okay, so I have the time derivative with respect to the fluid trajectory. I have the time derivative following the solid trajectory, which is actually very similar, but it gives me a different divergent term. Okay, so if I may recall a little bit of what happened last time. If I want to change the time derivative from the from the perspective of the fluid back into the solid, so what would happen is that I need to add back the convection term. Okay, do you remember? So let me write it out. So it's been a long time, so maybe may forget. So this is the trajectory over time for the solid. This is actually the trajectory time at the fluid. Okay, at this point, they actually overlap, but then they are moving in these two different molecules, they're moving into different parts, okay? They just meet and then they just move away from each other. Okay, now I want to take the derivative by following this relative to this. So there's a difference between the two. Okay, this difference is actually captured by the convection term. And so if I write it out, this term would be leading to the solid derivative of the porosity change times the gradient of the velocity. So this is actually the change of the porosity with respect to the solid time derivative plus the velocity, the Darcy's velocity times the gradient of the porosity. Okay, so this term is taking account of the difference between these two different trajectories, and hence this is actually the Darcy's velocity, which you may recall is the difference of the fluid velocity minus the solid velocity. Okay. Okay, so sorry, this is not the Darcy velocity, it's the relative velocity. I'm sorry for the terminology mistake. Okay, so this one, as we say before, I would need to do the same to change the perspective. I would actually write it again with respect to the solid derivative, and I have the relative velocity between the fluid and solid times the gradient of P. And this one also needs to be changed. What would that be is that I will have this as a velocity plus the relative velocity between the fluid and solid. Okay, now let me write it out. So Vs equals to V, and Vf equals to of course Vf, and the relative velocity is actually the difference between Vf plus the relative velocity is a Vf minus Vs. Okay, so Vf is actually equals to the relative velocity plus the Vs. Okay, do you get this? Let me write it out more. Maybe I make myself. Okay, so I have that Vf term. Vf obviously equals to Vf plus Vs minus Vs, right? Okay, you agree? Okay, and that will be equals to Vf minus Vs plus Vs. Okay, now this term gives us the relative velocity, and then the second term gives us the V. Now I take out the S because I'm following the solid trajectory. Okay, so that gives me that two term. Okay, so if I substitute this thing back and then combine equation 1 and 2, okay, I don't want to go over all the derivations, but if you like, you can try it at home. I just simply write out the results. I just don't want to keep writing during the algebra. Okay, so I will have so I will have the porosity times the divergence of the relative velocity equals to the Bill's coefficients times the divergence of the solid velocity plus the relative velocity times the gradient of F, gradient of porosity times the last compaction term. Okay. Now, one thing that is very important, if Ks approach infinite and Kf also approach infinite, okay, then what would happen? Okay, so this term would actually be gone, right? This whole term is gone, right? So, and then, of course, this will lead to B equal to 1, right? So B's modulus is also equal to 1. Now, if you actually, what happened is that if this actually happened, then what we would have is that we would actually have the only term that's right is the first three term, isn't it? Do you see that? Now then, let me write out this. Okay, let me put this term into this side, then I will have the plus, and then I have the V relative velocity times the gradient of F, and then plus V divergence of V equal to 0. Okay, so far so good. Okay, and then B of course equals to 1, so I'll just take this, just cross out this term. Now, if I combine this term, okay, if I actually applying the product rules, I would actually get back this term, divergence of the rho of the porosity times the velocity, the relative velocity equals plus the divergence of V equal to 0. So I'll get back what I have before, divergence of velocity times the divergence of Darcy's velocity equal to 0. Okay, now this one is actually Vf minus Vs, and as I said before, the Darcy's velocity is actually equals to this V overhead, and then that would be equals to the porosity of the material times the Vf minus Vs, which is actually the relative velocity. Okay? So we get back, so if in the special case, we get back our previous balance of linear momentum equations. Okay, so far so good. Now, we talk all the time about the balance law for the balance of mass for the compressible flow. How about the balance of linear momentum? How about the balance of energy? Okay, this also need to be changed because in this particular case, the effective stress principle also need to be generalized. Previously, what we cover is the Tasaki's effective stress principle, which actually apply to soil very well. It doesn't really apply to the soft material or even rock that well, okay? That is actually because in this particular case, if you actually look at the Earth example, what happened if you go to from the soil mechanic to the rock mechanic to the petroleum engineering is the following. As you actually change the application from a geotechnical engineering to mining to nuclear waste disposal or whatever, you keep going underneath the ground, okay? in this case, the lower the closer you are to the further apart from the ground, okay, the higher the higher the hydrostatic or overburden pressure, right? There's just more soil on top of it, and also it's hotter. Okay, this is actually the idea of the geothermal or actually energy pile or whatever, is that even though in a very cold region, the ground is freezing, but if you actually dig very deep, if you reach the subsurface, it will still be very hot, okay? That's why mining is actually very, very difficult. If you actually go under the ground, it will actually increase the temperature. Now, in this case, we need to actually consider the solid phase. The solid constituent is also compressible. And that we need to consider what is the consequence of having that additional compressibility implied to the internal energy. Okay, now I have more mode to store the energy, right? Okay. Now the energy per mass is actually the data change, which is actually the power per mass is related to the solid times the solid strength rate, okay? That's the fluid phase times the strength rate of the fluid, okay? Plus the total stress minus the individual part of the fluid times the solid skeleton strength rate. Okay, so the first two is just the individual phase. Sorry, I think I'm making a mistake here. Okay, so the first the first two terms are just the individual internal energy that are stored, and then the third term is actually coming from the effective stress principle. If you actually write out the conjugate term out, what we get is this. Okay, so far so good. And then that term is actually equals to minor porosity times Vf, identity double dot Vf minor Vs dot. Okay. Again, this whole term is actually just the fluid and fluid stress. The fluid won't have any shear stress. Okay, does that make sense? Okay, if you have shear stress, if you have shear modulus, then what Bruce Lee said about the water doesn't take any shape, take the shape of the container will not be true, right? If something have shear modulus. Okay. So you only have the volumetric term, you only have the pressure term, that's the right to the rhetoric term as 0, and hence you get this term. Okay, and this whole term, I double dot the strength rate difference between the fluid and solid is actually have another more convenience name is just the divergence of the relative velocity. Okay, I hope by far you get it. Okay, the divergence of the velocity is actually related to the diagonal term of the gradient term add together, and hence you get these expressions. Okay, so what eventually happened is that I have the first energy term that are actually related to the total stress, double dot the solid deformations, and I have the second term that are actually now relative to the relative velocity. Okay, and if I substitute to the previous derivations I have with regard to the relative velocity from the balance of mass, what I would have is that I won't write out all the details, but I will have the Buell's coefficients times the identity matrix double dot epsilon S PF plus PF with a very gigantic term that I have to write it out to complete the descriptions. Okay, now I will ignore the second term for a moment, but then the first two term here is actually very important because I will write this as my new argument for the total stress. And I write the second term PF blah, 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 as another energy conjugate. So this blah, blah is actually this. Okay, why is it important is the following. The effective stress is actually equal to the total stress plus BPFI right now. Okay, and this is actually from Noor and Bailey. 1971 is highly used in rock mechanics and is a generalized versions of the Tasaki versions of the effective stress principle. So this is the Tasaki's theory. Okay, and this is the Buell's theory. Okay, they are almost identical except the B. Okay, you see what I mean? So B equals to 1 for soil, for most soil. Okay, so B could be as low, usually could be within the range of 0.5 or 6, all the way to actually to 1 for rocks. Okay, for soft tissue, biological material, you will have a different B. And also sometimes the B, there's a new theory that B doesn't necessary to be isotropic. Okay, so B may not be a scalar, it could be a second order tensor. Okay, in this case, so what does that imply? If B is a second order tensor, so what will happen? So now B is actually is a scalar, or you can think about B times identity as a 3x3 matrix with only diagonal term, and all the diagonal terms are identical. But what if one of the diagonal terms are actually different than the other two diagonal terms? Okay, so what would that happen? Okay, now if you have a diagonal term and then all the eigenvalues of that matrix are the same, you can visualize it as a circle with all the radius are identical, right? Okay, if you have a diagonal term, you should still have a diagonal matrix, but one axis, one eigenvalue is much bigger than the other, then you would actually have an ellipsoidal shape, right? Okay, I don't know how to draw this thing properly. Okay, so what is the difference between a spherical object and an ellipsoidal object? Okay, it has a bias, right? Okay, so for a circle, does it matter does it make any difference if you rotate the circle? Okay, you look at the same circle. Okay, the shape itself is isotropic. This one is not. Okay, so if the B's coefficient is actually not even a scalar, so then you will have epsilon ij plus bij times pf. Then what it means is that p itself can actually lead to the that lead to derivatory stress or coupling. Okay, usually that won't happen, but let's say I have some metamaterial that are very complex structure. Maybe let's give an example. Okay, if I have a structure that look like that and my flow channel look like this. Okay, so in this side there's no permeability, and in this side there's a permeability. If the water is passing through, then it may actually trigger some shear. And just give some example. So in general, but in general, you were assuming that B is isotropic. Okay, now again, in the undrained conditions, I have Vf equals to V, and then I have the relative velocity and the downstream velocity both equal to 0, and then I will have the B of the divergence of V plus the rho plus the porosity divided by Kf B dot F equal to 0. Okay, so if I take this thing on the right hand side and write Pf as a function of the velocity, divergence of velocity, I minus bkf divided by rho f times the divergence of v, which we talked about before the break. Okay. Now here, but instead of putting these relationships into the balance of mass, I want to put it into the balance of linear momentum. Okay, and that is actually related to what we talked about before, if we remember the penalty term. Okay, what would I get here? Okay, now I have the P. I can rewrite P as a function of derivative of as the functions of the divergence of solid velocity, right? Isn't it? Okay, so sorry, this is P dot is actually equals to the bkf divided by porosity times the divergence of V. Now, if I assume this is small deformations and then the initial conditions is actually 0, I can integrating it, and then I will get the U. Okay, does that make sense? Okay, of course, assuming that the constant simply equal to 0, right? Okay, so if I substitute it back into the stress into the effective stress principle. Okay, the effective stress principle is actually the effective stress equal to the total stress plus BPFI. Okay, if I substitute this back, then what I would have is that I would actually have this total stress. I would actually have this total stress equals to the effective stress plus B squared KF divided by rho porosity times divergence of U times identity. Okay, so why do I care about this? Because this term is actually the CE double dot epsilon, okay, right? The first term. The second term is actually BSKF divided by rho F. So what is divergence of U times I? Well, it would be just the divergence of U in all the different axes, right? So I would have the, let me put the S here. Simply have the, I can actually simply add the identity and the identity of T double dot row S. Yes. And what I would eventually have is C plus B squared KF divided by rho F I double dot rho S. Okay, have you seen an expression like that before? So this look like just like a penalty term, right? If you add a Lagrange multiplier, if you want to introduce the incompressible constraint, then what would happen is that KF just need to be a very large number, right? Okay, so far so good. So now, if I put it back into the, consider the, I will still have this extra term, okay? That will allow a little bit of compactions, okay? But then that compression will compress when KF is actually going to infinite, okay? So in general, the K matrix will be much smaller than the KF, and KF is much smaller than the KS for most of the case. Okay, you see what I mean? So practically, even though you have incompressible material or slightly compressible material, oftentimes in solid mechanics, we're just assuming that the constituent is actually incompressible just for simplicity, because you will actually just make some small you will make some small error, but without sacrificing too much of the error. Okay, do you get the idea? Okay, from your undergraduates, consider the linear elasticity case. Okay, I have the effective stress equals to K minus 2 divided by 3 times the Name constant times the directions of U times identity tensor times this. Okay, so I would like to write the volumetric term separately. And then I would need to add the 1 divided by 3 because actually this whole thing is the mean pressure, right? Okay, you see what I mean? So, and then that one would be actually also, and then 1 divided by the chase of the total stress is actually equal to the Buck modulus times the velocity plus the additional term that I have. So as KF approaching infinite, the divergence VU would actually approaching 0 for undrained case, okay? And for undrained case only. And in this case, 1 divided by chase of the stress would be approaching BF, B squared KF divided by rho F times divergence of VU. Okay, this is actually very interesting because this term would be approaching infinite, while this term would be approaching 0. Okay, but then the mean pressure term is actually finite. Okay, you see what I mean? So you can actually give rise to the same system when you have incompressible elasticity. Okay. So what is the difference between incompressible elasticity and undrained system is that in the compressible case, you can still compress the material a little bit, okay? But if Kf go to infinite and then the water is actually trapped inside, then the whole thing become incompressible, at least according to the theory, okay? You will, okay? Do you see that? Okay, if it's undrained, okay, if it's undrained, then the Darcy's velocity equal to 0, then your incompressible balance of mass is simply divergence of V equal to 0, okay? But in the compressible case, cars you may let's see where is the to see the analog of a spring system, okay, with a pistol. And then there's a spring there, and then you allow water to come in and come out. Okay, and there's a very small tube. Okay, so and then this whole thing is filled with water. Okay, if you're compressing it, the material, so what will happen? Okay, the water would just shoot up, right? Okay, indicating the exit pole pressure. Okay. But over time, as you allow the water to actually dissipate, then the pole pressure would actually go down. Okay, now in the undrained case, let's say I shut down the outlet. Okay, I don't allow water to escape. Then when I'm passing it, then the only way to actually what happen is that the incompressible of the fluid will play a majority role of resisting the piston that pushing it down, right? Okay, so the exit pole pressure lost the ability to dissipate. Okay, does that make sense? Okay, because I don't allow any drain gauge. Okay. Now this could be a problem for solid mechanics problem, like for clay or salt or actual material that have very small permeability. Give example, if we give sufficient pressure, the water may move a couple centimeters per year. Okay, this is a very low permeability. Then the low permeability is associated with exit pole pressure keeping there for a very long time. Okay, so that can trigger a problem. Another possibility is that yes, okay, let's say there's a fault system, okay, and then you know what is a fault, okay, like if you're from San Francisco, you probably know there's a Hayward fault there, or if you're LA, San Angeles fault there, okay, so basically it's a line, okay, that are compressed in both sides, okay. So the earth itself actually have a tectonic pressure to push the two materials against each other, and there's a pole pressure there, okay. So if you actually know a little bit of plasticity or actually failure mechanism, this is the mean pressure. Okay, this is the territorial pressure, and then you're assuming that the failure envelope look like this. Okay, meaning that the more pressure I have, sorry, this is not the pole pressure, the solid pressure. The more pressure I have, the harder the shear, right? Okay, it's just like my hand. If I push really hard, I find it very hard to shear. Okay, if I don't have any force, I have a lot of freedom to move sideways, right? Just like against each other. Now, what happened is that previously we are stable, we're here. Okay, maybe I'll put a different point. We're here. Okay, very, very stable. I never reached the failure envelope. This is actually what happened in failure. So when you hit this, the whole thing slides. Okay, now I actually have a hydraulic fracture operations there. Okay, what is a hydraulic fracture applications? The hydraulic fracture applications is actually applied to the location where the permeability is very low, right? Okay, why do I actually want to apply the pressure in somewhere pressure that are very low? Because without fracturing the reservoir, I cannot extract any oil from it, right? Okay, you see what I mean? So I actually purposely add a lot of wastewater until the reservoir fracture. If it fracture, I increase the permeability, right? Okay, so what happened in between is that I will build up excess pole pressure. Okay, so the excess pole pressure will build up just like the spring, and I'm moving into these directions. Okay, so the whole total stress remain identical. Okay, but then the excess pole pressure is actually building up, so that my mean pressure, relatively speaking, is getting lower, right? You understand what I mean? So the total pressure is actually equal to the effective part plus the, sorry, let me use the consistent rate. The excess pressure is equal to the pressure of the solid, okay, which is actually a function of the solid part, actually minus the pole pressure of the fluid. Okay. Sorry. Okay, so now if I actually have a pressure, okay, this total pressure remain the same, but then the effective stress is actually changing because this thing is increasing, right? You see what I mean? So, or more accurately, I take the weight there, dot. If this one is not changing, then anything I gain from the change of the pressure will be in the equal and opposite side of the fluid pressure, right? Okay, you get it? Okay, now I'm moving it into these directions, and then eventually it actually hit this thing, and then there's actually a slide and that could occur. Okay, does that make sense? Okay, so if it's slide, it actually could trigger earthquake. This is actually in the last 10 years, people are actually questioning whether the operations of not just hydraulic fracture, but the storage of the CO2 can actually trigger the earthquake that otherwise won't happen. Okay, and you can also see those examples in Oklahoma. Oklahoma is not in a seismic active zone. However, there are lots of seismic activity that are actually getting records since the hydraulic fracture operations. Okay, so now this is just a hypothesis. Of course, there's a lot of debates on whether this thing happening. Okay, so far so good. Okay, so you get the idea. Now the important thing is that you will get the same theory, but then if you put the B there, then the B's coefficient become very important for assuming the safety of the system. Okay. So in the actual hydraulic fracture operation, you have a traffic light system. You're monitoring the pressure until it becomes dangerous, and then you stop. Okay, does that make sense? So that B become very important because you know at what point you need to stop the operations. The battery. Otherwise, you may underestimate it. Okay. Now let's put back into the finite element. We are almost there. Now the finite element implementations is actually very similar for the incompressible part and the compressible part. Okay. So the galvanic equations is remain the divergence of velocity, the divergence of the total stress plus the body force equal to 0. And then for the undrained case, I'm just want to put the undrained case first, because the difference between the undrained case and the drained case is simply the difference, the Darcy's law term. Okay, you see what I mean? So if I write one, you probably can get the other two, but then the undrained case is always the worst scenario, where it would, if you don't have the insert condition, it will trigger instability. Okay, so the first thing you may want to check is whether this thing works. Okay, in the undrained case, the relative velocity or the Darcy's velocity is actually equal to 0. So the balance of mass give me these simplified equations: the B's modulus times B's coefficient times the divergence of V plus the pressure term is actually equal to 0. Okay, so if you write it in finite element, what I would have is that I would actually lead to KD plus BG. G is actually what we defined before in the previous lecture. This is actually the matrix form of the balance of linear momentum. Now, what would be the balance of mass? The balance of mass would be B, G, T, D plus the MP. M is the new term that we previously doesn't have for undrained case. Okay, what would be the M? M would be coming from this term, okay? And then that would be coming from integrating this term into the, take out the time, that would be B times the direction of U plus the rho F, KF, P equal to 0. Okay, so what I would have is that I will have this M term is simply the check functions, transpose times rho F, KF times N, the integral of this. Okay, does that make sense? So if I write it in matrix form, I would have a K, B, G. B is just a scalar, okay? And then B, G, T, and then M. Okay, so far so good. Now you may also take out that this unknown and then simply write a penalty method. In this case, you simply need to modify the constraint as the following. You write the sigma equal to C plus B squared KF rho F I IT double dot epsilon. Okay, this would be actually the modified C, or actually let me use C for the penalty. Okay, so either choice will work, but then they will work in a different way. Okay, this you have to deal with the insert conditions. This one would look okay unless KF is very big. Okay, if KF is very big, what will be the issue? You may have locking. So, do you guys have covered the volumetric locking in the finite element course? Okay, let me give an example here. Imagine I have this element, okay, and then I'm fixing this, or maybe I even add this. Not the tip. Okay. Now this is, let's say, is volumetrically, let's say the volume change is actually equal to 0. Okay. Now I apply the force that are here. Okay. So how would they deform? Theoretically, if you don't have the finite element, it's deformable. Okay. So okay, it's deformable, but how would it deform? It will preserve the volume while we deform, right? And I'm pulling this in slightly different way. So I don't know what will be the shape. Maybe I don't know. Maybe something like this. Okay. Yeah. Sorry. Maybe some kind of shape changing like this. Now looking at the finite element, can I deform it? Okay. So look at this element. Okay. So this part is fixed, this part is fixed, and then there's a linear element, let's say. Okay, if it's a linear element, so can I actually move this point without changing the volume? I cannot, right? Okay, now this point is fixed. So now looking at this, now let's look at this element. Okay, now this point is fixed. Okay, I pin it down because I actually want to preserve the volume. Okay, and these two are actually also pinned down. Okay, so three of them pinned down. Can I move this element? I also cannot move this element. Now let's put it here. Okay, I just keep repeating the story. Okay, so this point is fixed. These 2 points is fixed. Can I move this point? I also cannot move this point, etc., etc., etc. Eventually, the whole thing cannot move. Okay, not now. Theoretically, it could move. Okay, because the shear modulus is finite. The bulk modulus is infinite, right? Okay, you get the point. Okay, so mathematical. So in a theoretical sense, this is just a very soft material where it's really hard to compressing it, but very easy to change the shape. Okay, so but in the finite element mesh, even the shear will be impossible. Okay, you see what I mean? Now, what happens if you use a quadratic element? Can I move now? Okay, how about I use a higher order polynomial? Okay, I definitely can move now. Okay, so now this is actually called the locking phenomena, and that can actually cause a solution that are incorrect. And it actually happens a lot when you have an incompressible material and you want to model bending. You would also see that the bending is incompressible, but strictly speaking, bending, locking, and the volumetric locking are actually a different thing. It actually requires different type of constraint. Okay, now if you use a linear finite element, what are the options for you to actually get the whole deformation working? Okay, I can use a polynomial, right? Okay, I can use a polynomial to make it work, but what are the other tricks that you can do to actually deviating the volumetric mapping, locking? Now there are other things people have attempted. For example, I actually just enforce the volume constraint of 4 elements. Okay, does that make sense? Okay, I would actually, instead of introducing the volume constraint everywhere, I'll just say that within that 4 elements, the average of them is actually equal to 0. Okay, that would actually weaken the volumetric constraint criteria and allow some movement. Okay, now there are also another case very common is coming from manipulating the Gaussian quadrature point. Okay, so you have a Gaussian quadrature point. This is actually very much related to this trick. Okay, so what it did is that the following. I have the directoric stress, and I also have a volumetric stress. I actually calculating them separately, and when I integrate the material, I would simply integrate this with a 1-point quadrature, and then this one with 4 points. Okay, this is actually a common trick that I use actually in Professor Tom Hill's book. It actually mentioned that. Now, why would that work? Why would that actually help the volumetric calculations? I undersampling the volume, right? Okay, so I actually just assuming that. So how would I actually integrating this? I just sample the center, right? Isn't it? And then I saying that the center of it times the volume will give me the volumetric term. Okay, so I'm also weaker. I create a bias in the rhetoric interpretations and the volumetric interpretations. Okay, now if I actually use, how about if I use one-point correlature for the rhetoric and the volumetric term? What will happen? So your integration would be less accurate, right? Okay, but what happened to when you actually have it less accurate? It may not be an issue except that you may lose the rank again, okay? And you can try it, okay? So this is actually having the MATLAB or having the Gaussian correlature benefit is that if you actually under integrate, you can actually compute the rank of the matrix. You will see that sometimes you lose the rank. Okay, so if you lose the rank, then what will happen? If you use the rank, then the Noon space AX equal to 0 would have some of the X that itself is not equal to 0. Okay, this is the definitions of the Noon space. Okay, so if you lose rank, then this thing could happen. And if that happens, what you have is also an instability. Instead of having a locking, you will have the instability mode. Okay, and then that mode could look like something like this. Oftentimes something like this. Okay, just like a contraction extensions, or checkerboard in some case. Okay, so checkerboard is just like this. Okay, so you have those incompressible mode where you actually coming from the Noon space mode. Okay, and you can actually put the Noon space and you will find that is consistent to this. Okay, so people have to find that, and then they can actually, sometimes they use the trick by directly determine what is the Noon space of that matrix and then apply artificial stiffness to it so that you get rid of it. Okay, so now even the kernel bases, even the space that are in the, even the basis for the Noon space will require some energy to trigger, and that can get rid of it. This is actually called the hourglass control. So you see this because it looks, sometimes people think that it looks like an hourglass. The hourglass, you know what's an hourglass? The thing that you put the sand there and you measure the time, it looks like this. So to actually get rid of that mode, you can actually have an hourglass control. The simplest way is to find out what's the kernel space and then apply some artificial stiffness to it. And then the most famous one is the one by Belinsky, the heads element with 1 point at the center with the hourglass control. So it become very famous because it's very cheap. For 3D element, you only evaluate 1 Gaussian point per element, so you have a very fine element, and you can have a very fine mesh that compute really fast. But then the problem is that you also need to find out the hourglass mode and then get rid of it with some artificial thing. Okay, now this doesn't necessarily apply to Poromechanics, but you can also apply the same idea in the Poromechanics. By the way, and then the Taylor hook is also one of the thing. You can apply the Taylor hook idea for actually cure the volumetric locking, have the rhetoric part using the higher order polynomial and have the pressure part and the pole pressure part both using a linear element, or actually at least using the lower order calculations. Okay, so that would also make sense. Okay. Okay, but the lesson to learn is that always check the always check the Noon space of your tangents, always check the condition number, and if the condition number is very high, or you have some kernel bases that are not 0, 0, 0, 0, 0, 0, 0, 0, 0, then you have to figure out how to get rid of it, okay? Otherwise, your system is guaranteed to be unstable, okay? So, in general, the K work. There's also another trick that I want to mention, and then I'll use. Okay, so this is a M, right? Okay, so they also sometimes what people did is that you assemble this matrix will give you an M matrix, okay? And it's not a diagonal matrix, but you can apply a row sum operator. Do you know what's a row sum operator? Okay, you're just saying that, okay, converges 1 to 1, 1 to 1 matrix into, you just add the row sum into the diagonal term. Okay, then you get a diagonal matrix. Okay, so what is the benefit of having a diagonal matrix M here and then a K here? So diagonal matrix, if P doesn't exist, okay, this thing will still be solvable. Okay, so you basically just change the you basically just change the you basically modifying the problem, taking out the consistency, but you actually get the a system that you can easily you may actually have better luck of having enough rank for the matrix. Okay, does that make sense? Okay, so there are better way to actually also ensuring that, and some stabilization idea is actually coming from ensuring that the M thing is actually work, like what we talked about in the last lecture. The weaker in-soup conditions idea is actually on simply modify M without modifying the B matrix to give you enough rank. Okay, so those are another story. Okay, so I think I go through the compressible part in one single lecture. Again, eventually it doesn't change that much in the final element implementation, just a lower